Consider the situation. There is a magnetic bar that is allowed to rotate around its center. Surrounding that magnetic bar, there are three stationary coils, A, B, and C, each one of them connected to a battery and a push-button switch, as shown. Now, we push the button associated with coil A, current flows, coil A becomes an electromagnet, and the bar will try to align itself with the coil, will start to rotate, and when it's about to be aligned with it, like so, we let go of the button. The current is cut in the coil, the electromagnet is no more, and inertia will carry the bar over. Now when the bar is halfway between coils A and B, I push the button of coil B. Coil B becomes an electromagnet, and now the bar will try to align itself with coil B, like so. When that bar is about to be aligned with coil B, I let go of the push button and let inertia carry the bar over halfway between coils B and C. At that point, I push the button of coil C, and then I repeat that again with A, B, and C. And by keep on pushing and releasing the three buttons of coils A, B, and C, I have created a rotating machine, a motor. I have created a situation in which a magnetic field is jumping from coil A to coil B to coil C and back to coil A. We have a rotating magnetic field, and the bar is chasing that rotating magnetic field in synchronism, rotating with that magnetic field. However, who in his right mind would want to spend days and nights just pushing and releasing buttons like that? We need to find currents that will turn on and off on their own. Those currents, of course, are AC currents. Let's see. That would be the current in coil A that will turn on at this point in time, reach a peak value, and then turn off at this other point in time. And we would apply another current like that to coil B, but delaying a little bit the time in which it turns on and reaches its peak, and another such current for coil C, but delayed with respect to the current in coil B. We have a set of three-phase currents feeding the stationary coils of the stator, and that way creating a rotating magnetic field, a field that is jumping from coil A at this point in time to coil B at this point in time to coil C, and then coming back to coil A. Let's see some names. The moving part of the machine is called the rotor. The stationary part, the part with the three coils, we call the stator. So we have three coils strategically located on the stator and carrying a set of three-phase currents, and with that we have established a rotating magnetic field. That is correct, an RMF. How fast does that field rotate? Let's see. At this point in time, the field is in coil A. At this other point in time, the field is in coil B. At this third point in time, the field is in coil C, and at this point in time, the field is back in coil A. So this is the time that it takes the rotating magnetic field to go through an entire revolution in the machine. How much time is that? In Canada, that is 1/60th of a second. So the rotating machine is turning about at a velocity of 60 revolutions per second, or what is the same, 3600 RPM, 3600 revolutions per minute. This is a motor that has only one speed, to be sure, and the speed is controlled by the frequency of the currents that we feed to the stator. In this machine, the rotor chases after the rotating magnetic field, keeping synchronism in its rotation with the magnetic field. We have created a synchronous motor. So, three phases imply a synchronous motor? Yes, but that is not all there is to it. Remember this one. When we have a flux that is cutting a wire, a voltage is induced in that wire according to Faraday's law. We remember that. And if there is a current path, that voltage will create a current. And once there is a current, the magnetic field will apply forces to that wire. And with forces, we have torques, and with torques, we have a motor. Let's see how we exploit this. Consider this scenario. The three stationary coils we've seen before, now in a 3D representation for phase A, phase B in blue, and phase C in yellow. If we apply a set of three-phase currents to those three coils, a rotating magnetic field will appear in the center of that setup. But now we bring a setup like this, a cylindrical setup with vertical wires like this one, and joined at the top and at the bottom with metallic rings, and connected so that it's allowed to rotate around its vertical axis. Let's see what's going to happen with those vertical wires connected by rings at the top and at the bottom. Let's remove the three coils to see more clearly what happens to that structure. The rotating magnetic field created by the three coils, red, blue, and yellow, is still there. It's rotating at a velocity of omega radians per sec. That field will cut those vertical wires and will induce a voltage, like so according to Faraday's law. But because there is a path for currents, the current will flow and the field will apply a force on those wires. And those forces, given the radius of rotation, will imply a torque, and the whole rotor will start to rotate following the magnetic field. Not quite as fast as the field, but fast enough. If it were to rotate at exactly the same speed of the field, there would be no more flux cutting, no more induced voltage, no more current, and of course no more torque. So that machine will rotate at a velocity that is slightly less than the velocity of the rotating magnetic field that we've seen before. If you imagine that rotor rotated 90 degrees, it looks indeed like a squirrel cage. That's why that type of rotor is nicknamed a squirrel cage rotor. And the whole motor around that is called a squirrel cage induction motor. Now in this case we have about 16 of those wires or bars, slightly skewed to be sure to avoid some other problem we haven't mentioned. You see those wires and the rings that connect them at the top and at the bottom. Now imagine that instead of 16 wires we had 50 or 100 or 1,000. What about if we had an infinite number of wires? We would have a continuous metallic surface surrounding that drum. Well, this is what I did. I set up a coffee can and put the coffee can in the middle of the three coils. Let me show you. In this experiment, instead of setting up a squirrel cage in the center of the machine, I put a coffee can. Yes, the coffee can works like a squirrel cage with an infinite number of vertical conductors. Three coils strategically located 120 degrees apart are fed by a set of three-phase currents fed from a busy hydro power outlet. A rotating magnetic field will appear in a moment, and that field will induce currents and will apply torques on the coffee can and make it turn about. Observe. It works just the way Tesla predicted it would. The currents produce a rotating magnetic field. The field induces currents in the can and applies forces on those currents. The coffee can rotates. Let's make sure there is nothing else making the coffee can rotate. If we have a peak inside the can, we ascertain there is no hidden mouse happily running around and making the coffee can rotate. There is nothing inside, and there is no hidden tiny electric motor at the bottom either. There is only a spindle, a passive spindle. What makes the coffee can rotate is the rotating magnetic field created by a set of three-phase currents in those three coils. And that is all there is to this experiment.